Hi, it's Mrs. Mafucci, and it's time for us to review gases in the kinetic molecular theory. We're getting ready for the STAR exam, so it's time for you to take out a piece of paper and take good notes as we review gases and the kinetic molecular theory. Let's consider, first of all, the general properties of gases. First of all, gases assume the volume and shape of their containers. Gases will expand to completely fill the container that they're in. Number two, gases are in constant, random, straight line motion. Number three, gases will diffuse. That means they go from a region of high concentration to a region of low concentration. Number four, gases have low density and they're easy to compress and to expand. And lastly, gases have mass and exert pressure. These are the general properties of gases that you should know for your exam. Let's consider Graham's law of diffusion. Well, first of all, we need to know what diffusion is. Diffusion is defined as the movement of particles from a region of high concentration to low concentration. Diffusion is always the movement from a region of high concentration to low concentration. Those brackets right there is how chemists abbreviate the word concentration. Whenever you see brackets, that means concentration. Don't use parentheses, use the brackets. Parentheses do not mean concentration. What this means is that if I open a bottle of ammonia, just to remind you, ammonia solution is gaseous ammonia in a solution of water. Now, when I open up the bottle cap of ammonia, the cap allows the gaseous ammonia to escape from the bottle, and it's going to go from the region of high concentration, the bottle, and then it will spread out throughout the classroom, and eventually you'll be able to smell the ammonia. Now, the greater the space between particles, the faster the particles are able to spread out. What that means is that gases diffuse faster than liquids, and liquids diffuse faster than solid. The important thing about Graham's law of diffusion is this: that the rate of diffusion is inversely proportional to the mass of the gas. What that means is this: as mass increases, the rate of diffusion decreases. What that means is that greater mass particles, or particles with a greater mass, are going to diffuse more slowly. The greater the mass, the slower it diffuses. So if I give you a problem on the test, or let's say the California STAR exam asks you a question such as, which of the following gases will diffuse most rapidly? You're going to pick the smallest molecular weight gas. Lighter gases diffuse faster than heavier gases. Let's consider the following experiment. We're going to see the ammonia come from the left side and the hydrogen chloride on the right side.
Diffusion is the process whereby molecules of gas move to completely occupy a space, giving a uniform partial pressure. In this example, gaseous ammonia and hydrogen chloride diffuse through air from either end of a sealed tube. When the two gases meet, a precipitation reaction occurs, forming ammonium chloride. The mass of the hydrogen chloride molecules, relative to those of ammonia, is greater. Thus, hydrogen chloride molecules travel more slowly.
So from this experiment, on the left side is the ammonia. Let's think about it. Ammonia has a weight of 17 grams per mole. Hydrogen chloride, which is on the right side, has a mass of 36.5. That means ammonia is going to travel further down the glass tube than the hydrogen chloride will, which means that the product, ammonium chloride, which is that white precipitate that you see forming in that tube, is going to form closer to the hydrogen chloride. Remember, the rate of diffusion is inversely related to the mass of the gas particle. The greater the mass, the slower it diffuses. Let's now consider the kinetic molecular theory. We're going to look at 5 assumptions. Number 1, gases are composed of small particles that are in constant random straight line motion. Number 2, the volume of individual gas particles is negligible compared to the volume occupied by the gas. What that means is this. The size of a particular molecule does not determine the volume of a gas sample. Remember, gases expand to completely fill their containers. So what we're saying is that the size of an individual gas molecule is small, insignificant, negligible compared to the total volume that the gas will occupy in a container. Now, gases expand when heated. The individual gas particles do not increase in size. What happens when you heat up a sample of gas is that the gas has more kinetic energy and can spread out and move faster. Now, the third assumption of the kinetic molecular theory is that there are no attractive or repulsive forces. In other words, the attractive and repulsive forces between gas particles are negligible. We are going to totally ignore intermolecular forces of attraction, such as van der Waals. We're going to pretend that they do not exist. Number 4, we're going to assume that the molecular collisions are perfectly elastic. So when gas particles collide with one another, there's no loss of energy. The energy is transferred, but is not lost. The last assumption is that the average kinetic energy of the gas particles is directly related to the absolute temperature. Remember, in this unit, we're always going to do calculations with temperature in the Kelvin scale. That's called the absolute scale. In order to change Celsius to Kelvin, you add 273 degrees. Absolute zero is the lowest possible temperature. 0 Kelvin is absolute zero. In this picture, we see that as the absolute temperature increases, the speed of the particles increases. Lower average kinetic energy means that you're at a lower absolute temperature. On the right, the higher average kinetic energy is a result of the higher absolute temperature. Now, an ideal gas obeys these 5 assumptions. However, there's no such thing as an ideal gas. Instead, we're working with real gases. So how can we make a real gas obey the rules of the kinetic molecular theory? If a gas is at low pressure and high temperature, this will help real gases behave more ideally because there will be fewer, yet faster collisions. Fewer collisions because at low pressure the volume is greater and there's going to be more distance between the gas particles. And the collisions are going to be faster because you're at a higher temperature, which means that there's going to be a less chance of interaction between the gas particles. In other words, we're looking for a way to reduce the intermolecular forces of attraction. Low pressure, high temperature. Now let's consider what pressure is. Pressure is defined as the force dispersed over a given surface area. P equals F over A. What this means is that if the force is acting over a large area, such as me standing on a pair of skis, the force is my weight, the surface area is the area of the skis touching the snow. Let's see what happens. Force divided by a large amount of area is going to give us very little pressure, which means I'm going to glide down the hill real easily. Now, If the force is acting over a small area, such as me standing on some ice skates, all of my weight is being distributed to that thin blade on my skates. That's going to give me the same amount of force, but the area is going to be tiny. The denominator is going to be tiny, which means we have a lot of pressure. In fact, that's what ice skating is. You're causing so much pressure by that blade on the ice that the ice begins to melt, and that's why you're able to ice skate. Pressure depends on how hard, which is proportional to the mass and speed of the particles, and how often the molecules strike the wall. Standard pressure is defined as 1 atmosphere, 760 millimeters of mercury, 760 torr, or 101.3 kilopascals. That means they're all equal to each other. Why are there so many different units when it comes to gas pressure? Well, it depends on the kind of scientist you are. Chemists prefer using atmospheres. Physicists prefer to use kilopascals. And weather people, well, they like 760 millimeters of mercury. Now here's an example of gas particles striking the walls of their container. The harder the collisions with the wall, and the more collisions with the wall, the higher the gas pressure. Now let's consider atmospheric pressure. Atmospheric pressure is the force of gravity on the atmosphere, and it's measured by a barometer. If you look at this diagram, you see that the air pressure is pushing down on that mercury, and it forces the mercury to go up that column. Now, the higher the air pressure, that means the stronger the force is pushing down on that column of mercury, the higher it's going to go up. Now, we would stick a ruler on the side of that glass tube, and we would measure the height to which the mercury rises. Do you see now why scientists who study weather will use millimeters of mercury to describe the atmospheric pressure? Because you're measuring the height of the column in millimeters. Now let's consider Dalton's law of partial pressure. John Dalton not only came up with the atomic theory, but he studied the effect of gases in a mixture. Now, the partial pressure of a gas is the pressure exerted by a single gas in a mixture. It's as if that gas alone occupied the container. The total pressure of a mixture of gases is equal to the sum of the partial pressures. The bottom formula is saying that the total pressure is equivalent to P sub A, that means the partial pressure of A, plus P sub B, the partial pressure of B, plus P sub C, which is the partial pressure of C, and so on. So the total pressure is equal to the sum of the partial pressures. So let's take a look at this diagram. We have some gases in the first container that has a certain amount of pressure. Now in the second container, there's a different gas exerting a different amount of pressure. When we combine them into the same volume container, okay, do you see that? The volume and temperature are constant. The total pressure is equal to the sum of P1 plus P2. Now, let's look at this problem. If the total pressure in this mixture of hydrogen, helium, and neon, if the total pressure is 10 atmospheres, and we know that the partial pressure of helium is 2, and the partial pressure of neon is 5, we can definitely calculate the partial pressure of hydrogen gas. Helium is 2, plus neon is 5, plus we need to know hydrogen so that when we add it all together, we're going to get 10. So it makes sense that hydrogen has a partial pressure of 3 atmospheres.